Hello friends, our next topic is phase locked loop, or in short PLL. For the demodulation of FM wave, PLL is widely used today because of its low cost and superior performance, especially in the situation of low signal to noise ratio. PLL is a simple closed loop feedback system. In practice, phase lock loop is widely used as indirect frequency demodulation as well as carrier synchronization. And on the basis of designing, PLL consists of voltage controlled oscillator, multiplier and loop filter, that is a low pass type. The main function of voltage controlled oscillator is to perform frequency modulation on its own signal, that is called control signal. The output of VCO is multiplied by the incoming FM wave with the help of multiplier. The output of the multiplier, that is called error signal, and it contains both low frequency and high frequency components. And by using loop filter, that is a low pass type, removes the high frequency component and allow to pass only low frequency component. And this low frequency component correspond to the modulating or message signal. Now we discuss PLL in brief with the help of equations. Before this, we assume that the voltage control oscillator is adjusted in such a way that when the input Vt called control signal is 0, two conditions must be satisfied. First is the frequency of VCO, that is called free running frequency, must be set to the carrier frequency, and the second is the output of VCO, that is RT, has a 90-degree phase shift as compared to unmodulated carrier frequency. In phase lock loop, the main function of VCO is modulation process. Here, VCO generates its own FM wave using control signal Vt, that is called locally generated FM. This locally generated FM, denoted by RT, is multiplied by the incoming FM wave, that is given by ST, and it is equals to AC sine 2 pi FCT plus phi 1t, where phi 1t equals to 2 pi kf integration m tau d tau. Here, AC is called carrier amplitude and kf is called frequency sensitivity of the modulator that is responsible for the generation of FM. Now, as voltage control oscillator generates its own FM wave, that is called locally generated FM and denoted by RT, that is equals to A suffix V cos within bracket 2 pi FCT plus phi 2t, where phi 2t is equals to 2 pi kV integration V tau d tau. Here V tau is called control voltage. Also, A suffix V is simply an amplitude and kV is the amplitude sensitivity factor of the voltage control oscillator. So, the incoming FM wave and locally generated FM get multiplied with the help of multiplier and produces an error signal, that is E function of t. Now we note a point. The main function of feedback loop that contains a VCO is to adjust the angle phi 2t such that it becomes equals to phi 1t. So the main function of feedback loop is to adjust the angle phi 2t equals to phi 1t. Now the output of the multiplier is error signal, which is equals to AC sine 2 pi FCT plus phi 1t into AV cos within bracket 2 pi FCT plus phi 2t. Here the first expression is incoming FM wave and the second one is the locally generated FM wave. So here we have product of two functions, that is sine and cos function. So we can use formula sine A cos B, that is equals to 1 upon 2 within bracket sine A minus B plus sine A plus B. And after using this we get error signal. that is Et equals to AC AV upon 2 within bracket sine phi 1 minus phi 2 plus sine within bracket 4 pi FCT plus phi 1 plus phi 2. And here we introduce a multiplier gain which is equals to 1 upon 2 and call it K suffix M. So in place of 1 upon 2 we can write K suffix M, that is called multiplier gain. And after this arrangement we have two terms. First term corresponds to phi 1 minus phi 2, that is called low frequency component because it is the difference frequency term, and the second is 4 pi FCT plus phi 1 plus phi 2, that is called high frequency component because it has double frequency of 4 times of Fc. As the multiplier output contains both high and low frequency terms, and our interest is only in the low frequency term because the loop filter is a low pass type. After neglecting high frequency component, we have low frequency error signal, that is equals to Km AC AV sine phi suffix E, where phi suffix E is equals to phi 1 minus phi 2. And in place of phi 2 we can write 2 pi kV integration V tau d tau. So by using this error signal we have a condition. When phase error angle is equals to 0 radian, the PLL is said to be phase locked. Also, when the phase error angle phi E is less than 1 radian, the PLL is said to be in near phase lock. So, on the basis of this approximation, we can write sine phi E is approximately equals to phi E. That is called approximate value of phase error angle. And this approximation is valid or accurate within 4%, provided that the error angle is less than 0.5 radian. So the approximate form of error signal is given as Et equals to Km AC AV into phi E. And here we introduce a new parameter of PLL called loop gain parameter, denoted by K0, and its value is Km kV AC into AV. So accordingly, error signal in terms of loop gain parameter is given by Et equals to K0 upon kV into phi E. And now this approximate error signal is applied to the loop filter and it produces an output V function of t. For this, let us consider this loop filter as a type of LTI system with impulse response ht. And we know that the output of any LTI system is given by the convolution of input signal and impulse response. So for PLL, output Vt equals to convolution of error signal and impulse response ht. And its formula is integration E tau ht minus tau d tau with limit tau equals to minus infinity to infinity. And this equation constitute a linearized feedback model of PLL. So in order to get output Vt, we consider loop filter as LTI system. Also in phase lock mode, the error angle is equals to 0, and in near phase lock, the error angle must be less than 1 radian. Now again, we consider an error signal, that is E function of t equals to K0 upon kV into phi suffix E. Here phi E is equals to phi 1 minus phi 2, where phi 1 is the angle of the incoming FM wave and phi 2 is the angle of the locally generated FM wave in voltage controlled oscillator. And since there is a negative sign with phi 2, that is feedback phase angle, so we can say that there is a negative feedback of closed loop PLL system. Also, the output of PLL is given by the equation which represent linearized feedback model. So we can use the linear feedback theory. according to this theory, when the open loop transfer function of linear feedback system has a large magnitude compared to unity, then the closed loop transfer function of the system is effectively determined by the inverse of the transfer function of the feedback path. So to explain this, we assume a negative feedback amplifier having mu as transfer function of forward path and beta as transfer function of feedback path. And the gain of this negative feedback amplifier is capital A equals to mu upon 1 plus mu beta. And according to linear feedback theory, as open loop transfer function, that is mu beta, is greater than 1, then the approximate gain of the system is 1 upon beta. Here 1 is neglected as compared to mu beta. And accordingly, mu is cancelled and we have inverse of the transfer function of feedback path, that is 1 upon beta. Now, we are going to apply this theory on our PLL model. For this, we represent linearized feedback equation using block diagram, that is shown in figure. There is a negative feedback because we know that the error angle phi e is given by phi 1 minus phi 2, where phi 1 is the angle of the incoming FM wave and phi 2 is the angle of locally generated FM wave in voltage control oscillator. So there is a negative sign with phi 2 and we have a negative feedback system. And according to the equation, the angle phi 2 is equals to 2 pi kV integration V tau d tau. Here V tau is the control signal. So in PLL, feedback path having voltage control oscillator, and here to get angle phi 2, we take transfer function as integration of d tau with limit 0 to t. In this, the input signal is Vt, that is a control signal. So the output of this transfer function is integration of V tau d tau with a limit of 0 to t. And after multiplying with 2 pi into kV, we get 2 pi kV integration of V tau d tau. That is the value of phase angle phi 2. Next, for the forward path, error signal is equals to k naught upon kV into phi 1 minus phi 2. And according to the given equation, here k naught is called loop gain parameter and its value is km into kV AC into AV. So, as angle of error signal, that is phi e equals to phi 1 minus phi 2, and after multiplying with k naught upon kV, we get error signal, that is k naught upon kV into phi 1 minus phi 2. Also, in forward path, there is a loop filter with impulse response ht, and output of this loop filter is the convolution of input error signal and impulse response ht. And here the main function of the feedback loop is to adjust angle phi 2 equals to phi 1 in order to get zero error signal. So, for the linearized feedback model, we observe 3 points. First point is, the feedback path is a scale integrator, and according to the theorem, the inverse of this feedback path is described by the scaled differentiator, that is in time domain. So the approximate output Vt is equals to 1 upon 2 pi kV into d phi 2 upon dt, where phi 2 is equals to 2 pi kV integration of V tau d tau. So the feedback path get inverse and we have differentiation of phi 2. Second point is, in PLL, the feedback loop adjusts angle phi 2 equals to phi 1. So we can say that the closed loop behavior in PLL in time domain is described by the overall output V function of t, and this output is produced by the incoming FM wave with phase angle phi 1. So the approximate form of PLL model is shown in figure. Here the output Vt is produced according to the incoming FM wave having phase angle phi 1. So after adjusting phi 1 equals to phi 2, we get output Vt according to the phase angle phi 1. And in approximate form of PLL model, we assume that the loop gain, that is K naught, is greater than 1. And according to the third point, the magnitude of open loop transfer function is controlled by the loop gain parameter, that is K naught, and it is equals to Km into Kv AC into AV. So after observing these 3 points, we have linearized model of PLL. In this, the loop gain parameter is used to adjust the angle phi 2 equals to phi 1, and this happens when we take loop gain parameter K naught far greater than 1. So when K naught is greater than 1, and under this condition the phase error angle phi e tends to 0, and we get phi 1 equals to phi 2. And after phase adjustment, we relate overall output Vt by the approximate formula in terms of phi 1, that is V function of t equals to 1 upon 2 pi kV into d phi 1 upon dt. And according to this equation, the closed loop transfer function of PLL is effectively determined by the inverse of the transfer function of feedback path. Now, in place of phi 1, we can write 2 pi kf integration of m tau d tau. So, differentiation and integration cancelled. Also, 2 pi is cancelled out, and we get Vt equals to kf upon kv into mt. So here, output Vt is directly proportional to scaled message signal. So, in order to recover original message signal except scaling factor kf upon kv, PLL must operate in phase lock or near phase lock mode with a very large loop gain parameter K naught compared to 1 radian.